Time for more practice with problems which involve the chain rule. Such an important rule. So you want to make sure you practice it so it just becomes completely second nature. You want to know it like you know the back of your hand. See, yeah, that's the back of my hand. Now you want to know it like the back of your hand too, which means, of course, practice. And in particular, you need to be doing the practicing. So do as much of these on your own as you can before coming to watch the video. I hope you do watch these videos because they might give you some different perspectives and ways to help you avoid getting stuck. Now, if you are watching them and you haven't finished the problem, make frequent use of that pause button. Only go as far as you need to get unstuck, and then keep taking your calculus journey on your own because, well, it's a beautiful journey and you want to be able to experience it all so you can tell your kids and your grandkids about the fun times you had exploring calculus. Well, let's begin. Suppose the line y equals 5 minus 3x is tangent to y equals f of g of x at x equals 1. F of x is invertible, and we have the following information about f of x. And the question is, find the tangent line to y equals g of x at x equals 1. Well, isn't that interesting? There's a new word we haven't really seen before, but we will be seeing a lot more in a future session, which is invertible. That's a fun way of saying it has an inverse. Okay, well, how will that come into play? So, what do we know? Well, we know that this line is a tangent line. Whenever you have a tangent line, that means we have information. In particular, we understand what the function is at 1 and what the derivative is at 1. Now, what's our function? Well, our function is f of g of x. And therefore, since we have our tangent line at 1, we can say that f of g of 1 is equal to whatever this line does at 1. So if we plug in 1, we get 5 minus 3. So f of g of 1 is 2. All right, that's good to know. And what else do we have? Well, we need to know something about the derivative, right? So first off, what's the derivative? Y prime. That's f prime of g of x times the derivative g prime of x. That's just the derivative at any point. Now, we know something about the derivative at 1. So that's f prime of g of 1 times g prime of 1. And we're told, well, that has to match what's going on here. So, what's the derivative at 1? Is it 5? Be careful. See? Normally we write the line y equals mx plus b. See, they wrote it like b plus mx. So the slope is what's attached to the x. This may not be the first number. So in our case, the slope is negative 3. So we're told that the derivative is negative 3. Okay, so that's what the tangent line tells us. Now, what do we want? We want the tangent line to g of x at x equals 1. So in particular, that tells us what we need. It tells us that we need to know what is g of 1 and what is g prime of 1. See, if we have those two pieces of information, we have our line. Okay, so let's start thinking. Well, let's start with our fact that we know f of g of 1 is equal to 2. How can we use it? Well, we know that our function is invertible. What does that mean? Well, it means that if I have any output, I only ever achieve that output once. So in other words, I never have the same output twice. So what I can do is I can start scanning and say, do I have my function ever equal to 2? And I say, well, I do have a place where my function equals 2, namely at the point 3. So since I have f of 3 equals 2, and it's invertible, that says, look, the only way this is possible is if the g of 1 has to be 3. So that's where we used invertibility. So we've now been told g of 1 equals 3. All right, what else can we say? Well, we need g prime of 1, and look, there's a g prime of 1 right there. So let's dig into this. So we have f prime of g of 1, but I now know g of 1 is 3. So f prime of 3 times g prime of 1 has to be negative 3. So what is f prime of 3? Well, according to this, f prime of 3 is 2. So 2 times g prime of 1 has to be negative 3. All right, so that lets us say what? Well, let's just say g prime of 1, if I divide by 2, is negative 3 halves. So there we go. There's negative 3 halves. And now, we've now found what the value of the function is at 1 and what the value of the derivative is at 1. And that's actually what we need to know. So once we know those two pieces of information, we can say, aha, we've made progress. So, in particular, we say we've got our point and our slope, right? So, y minus our y value, which is the 3, is equal to our slope, negative 3 halves, times x minus our x value, which is 1. It even says it right there, 1. And so, what can we do? Well, y equals negative 3 halves x. Notice this will become a plus 3 halves plus 3 more. So plus 3 halves plus 3 more will make this plus 9 halves. And there you go. There's the answer. All right, good, nice, fun problem, fun problem. Like I said, invertibility, we'll do more with that in the future. Okay, well, here's a function. It's piecewise. So f of x is this function. It's x squared sine 1 over x if we're not 0, and it's 0 if we are 0. Now we can actually kind of roughly sketch what this function does. Because we know that the sine 1 over x, what is that doing? Well, it comes, but as we head towards 0, it starts to oscillate a lot. So that has that sort of crazy oscillation at 0. Now, when you scale it by x squared, excuse me, what happens is instead of oscillating between plus 1 and minus 1, so instead of going up and down, what it'll do is it'll oscillate between x squared and minus x squared. So our curve would have something like the following. So I have a positive x squared here, just put a dotted line, negative x squared there, dotted line, and what we see is that we'll come in and we'll oscillate a lot as we come into 0. Okay, so there we go. That's our function. Okay, so here we go. Part A. Well, it says find f prime of x for x not equal 0. Now, that's easy. See, if x is not 0, what it's really saying is take the derivative of x squared times sine 1 over x. So for part A, what we're really asked to find is take the derivative of x squared sine 1 over x. Now, what do we see here? Well, we see a product rule and a chain rule because 1 over x is inside our sign. Now, I should note before we get too far along, 1 over x, a nice way to think about it, even if we don't write it, but I'm going to go ahead and write it, is as x to the negative 1 power. So, let's do our rules. Product rule. We're going to take the derivative of the first, so that's 2x times the second, sine of x to the minus 1, plus, now I'll take the first, x squared, times the derivative of the second. So, derivative of sine, cosine, inside stays the same. X to the minus 1 times the derivative of the inside, minus 1 comes down, x to the 1 smaller power, x to the minus 2. We're going to clean it up a little bit. Now, how can we clean it up? Well, we get our 2x sine of 1 over x because x minus 1 will go back to 1 over x. Now, x squared and x to the minus 2. What happens to that? Well, they cancel. See, this is a x squared. That's a 1 over x squared. So they cancel each other, and then you're left with minus cosine of 1 over x. Okay, so now that's part A. We're done with part A. We found our derivative. Here it is. Interesting stuff, interesting stuff. Well, let's look at part B. Now, again, this is derivative away from 0. So we can say, well, that's what's happening away from 0. So let's look at the limit as we go to 0. So that would be 2x sine 1 over x minus cosine of 1 over x. Now, I'm not going to spend too long on this, but here's the important idea. In the first piece here, we have this part is going to oscillate between plus minus 1. Then it's going to say that this part goes to 0. So if I have something which is going up and down between plus 1 minus 1 times something which is getting small, what's happening is it's oscillating, but it's making smaller and smaller oscillations to the point where it's imperceptible. So that as a net combination, this is getting small. So this is an application of the squeezing theorem, or sandwich theorem, if you like. So the first part gets small. What about cosine of 1 over x? What does that do? Now, sine 1 over x, we said, oscillates more and more. But what about cosine? Well, maybe it co-oscillates. Well, actually, it just does the same thing. It's still trying to get infinitely many up and down patterns inside the cosine squeezed in between 0 and 1. So what happens is this has that same does not exist. It doesn't converge to any particular thing. It just sort of is going all the way up and down, infinitely close. When we say infinitely close, we mean arbitrarily close to 0. So the limit is, it doesn't exist. Okay, so there is no limit. All right, so that's B. So we found the derivative and said, hey, when you go to 0, the limit doesn't exist. Now, for part C, well, we just finished part B. And we said, hey, the derivative, as you take the limit to 0, it doesn't exist. And now we're asking, well, what's the derivative of 0? What does intuition say should be true? Our intuition says, there is no derivative at 0. Okay, be careful, because sometimes intuition can be right, and sometimes it can make you go like, what? Maybe this is one of those moments. Let's find out. So, how do we find the derivative at 0? Well, the answer is there's an actual rule for finding the derivative at 0. So, here we go. What's the rule? It says the derivative at 0 is equal to the limit as h goes to 0, f of 0 plus h minus f of 0 all over h. Okay, that's just a definition. Good to know. Now, the nice thing is that f of 0 is 0. So that's going to go away. And then notice here we have f of h. So that's going to become this part with h squared sine 1 over h. I'm dividing by h, so this is the limit as h goes to 0. And if we just go ahead and cancel off one of those h's in the front, we're going to get h sine 1 over h. Now, what happens? Well, we know, if we look at the previous, what we just said, this is our oscillating, and oscillates between plus minus 1. This part goes to 0, so if we combine them, so I have something that might be going up and down, but it doesn't go very far, times something getting small, getting tiny. The net result is it goes to 0. And again, this is the squeeze theorem. What? So, we see that there is a derivative at 0, and it's equal to 0. In some sense, it's not surprising, because it's saying like, well, our derivative should be the x-axis, because that's what the picture says. But what do you see? Well, it says what? Well, so the derivative exists everywhere because, lo and behold, we can compute it at 0, we can compute it at not 0, but the derivative is not continuous. What? Oh my gosh. So if you've ever wondered, why mathematicians bend over backwards to be like, okay, we got to be really careful about what's true and what's not true, it's because of problems like this. Because we've been burned in the past. Things that look like they should be straightforward and easy or obvious can, in some really weird cases, turn out to be not so clear and not so obvious. So we got to be careful. That's why we do the work. Do the work. Interesting. Interesting stuff. Wow. Nice. All right. Well, let's try another problem. So, let f and g be differentiable functions. Differentiable means we can take a derivative, and they satisfy the following. So we have this big table here, and we have that h of x is f of g of f of g of x. Okay, so it's a function and a function and a function and a function. Ooh, 4 layers in this onion. Find the tangent line to h of x at x equals 1. Now, of course, we know that find the tangent line to h of x at x equals 1 really is code for we really need to find h of 1, and we need to find h prime of 1. Well, let's start with the h of 1. That's almost always the easier one. So according to the rule, this is f of g of f of g of 1. Okay, so time for us to perfect our table reading skills. So we come here and just start. And when you're doing this kind of evaluation, we're going to evaluate from the inside out. So we start with g of 1. Well, here's g of 1. That's 2. Then we go to f of 2. So f of 2 is 3. Then we go to g of 3. So g of 3 is 1. So now we're going to go to f of 1. Well, that's 52. Okay, good. So we found our point. And notice it was just a very careful work from the inside out. What is g of 1? Okay, 2. So then what's the next layer? F of 2. And then what's the next layer? So forth and so on. Now, h prime of 1, well, how are we going to find that? As a first step, we need to say, well, what is h prime in general? So, let's see. According to our rule, this is going to be a chain rule. So, take the root of the outside. F prime of, leave the inside alone. Okay, there we go. Root of the outside, leave the inside alone. Times by the derivative of the inside. So, in our case, the inside has sort of, instead of 4 functions, we've peeled one off. So it's now 3 functions nested. So the next layer is g prime of f of g of x. Okay, are we done? No, because now we've got to times it by the derivative of the inside here. Okay, so what's that? Well, it's going to be f prime of g of x. Are we done? No, because we got to multiply by the inside again. Okay, so what's the derivative of the inside? It's g prime of x. Are we done? Well, yeah, we are. Now you might say, can we go one more layer? Come on, one more. Well, you could. You could say, okay, x is now my inside. And what's the derivative of x? 1. You could do that. It's not wrong, but it's not helpful. But, if you were like, oh, one more, then, well, hey, it's possible. It's possible. So, what do we get? So that tells us that h prime of 1, I don't know where that came from. That's f prime of g of f of g of 1, and times g prime of f of g of 1 times f prime of g of 1 times g prime of 1. Now, let's go through and mark what all of these are. We actually have some help here. We know what g of f of g of 1 is, because that was our sort of our last thing we plugged in, right? That turned out to be 1, so this is really a 1. We also know what f of g of 1 is. That's the 3. We know what g of 1 is. That's the 2. And we also know what 1 is. Spoiler alert, it's 1. Now, if you're wondering where I'm getting these from, I'm getting them from here. See, g of 1 is 2. F of g of 1, we said, hey, that was the 3, and so forth and so on. So, now we say, okay, we need to find out what these values are. F prime of 1. So I come along. F prime of 1 is 2. So we have 2. G prime of 3. G prime of 3 is negative 5. And then we have f prime of 2. So f prime of 2 is negative 3. And then we have g prime of 1. G prime of 1 is 2. All right, so 2 times negative 5 times negative 3 times 2. Well, the good news, we have two negatives, which make things positive. So it's a positive number. If I multiply 2 times 5, that's 10. 3 times 2 is 6. So put that together, we get 60. Okay, so h prime of 1 is 60. There we go. Now I know what the value of the function is, and I know the value of the derivative. So I put these two pieces of information together, and I can say that y minus the y value, 52, is equal to our slope, 60, times x minus the x value, which is 1. Or we could say y equals 60x, then subtract 60, negative 60, add 52. Negative 60 add 52 is minus 8. And that is our tangent line. And there you go. Good stuff, good stuff. Good. Layers. Onions, right? Lots of onions here. Okay, on to the next one. And our next problem, another good one. Okay, so suppose we have a function and it's twice differentiable. Just as another fancy way of saying we can take derivatives 2 times. And it satisfies the following. So we know information about what happens at 2, and then what happens at 3, and what happens at 4. So we know something about this function. Now the question is, what's the second derivative at 1? Where our function is x squared times f of x squared plus 2x. Wow. Okay, I can sense there's going to be a lot of careful computations ahead of us. Well, okay, so we don't need to rush anything. We know what we're doing. We know we're looking for g double prime of 1. So a natural first thing to do is say, hey, let's find g double prime of x. And then once we've found that, we'll plug in x equals 1. Good. That's what you want to do. So the way to get to g double prime is get to g prime, which means we're first going to take a derivative, and then we'll take another derivative. And when we're taking derivatives, what rules are we going to need? Well, the chain rule, because we see x squared plus 2x is inside the function f, and the product rule, because we have a product of two things. All right, so let's go through it carefully. So we'll start with the function. G of x is x squared f of x squared plus 2x. Now we'll take our first derivative. All right, so nothing too surprising. So we'll start with the product rule. We're going to take the derivative first, which is the derivative of x squared is 2x. Leave the second alone, f of x squared plus 2x, plus the first, which is x squared, times the derivative of the second, and this is where we need to do that chain rule. So it's the derivative of the outside, f prime, inside stays alone, times by the derivative of the inside. So times by 2x plus 2. All right, now that is the correct derivative. Now, we know we're going to take another derivative. So if you know you're going to do something with the expression, the best and most ideal thing you can do is say, let me clean my expression up. Let me make it easier to work with. So this would be, here, the only thing that I can really see that makes it easier to work with is you multiply the x squared and 2x plus 2. So we still have 2x f of x squared plus 2x, then plus x squared times 2x plus 2, that's 2x cubed plus 2x squared times f prime of x squared plus 2x. Okay, now we're ready for our third derivative. All right, so g double prime of x, and here we go. So come to the first part. So the derivative of the first, so that would be 2 times the second. So f of x squared plus 2x plus the first, 2x, times the derivative of the second. So chain rule. So take the derivative f prime of x squared plus 2x, and don't forget, times the derivative of the inside. So times a 2x plus 2. Okay, so we did the product rule, chain rule. Okay, now we come to the next term, plus, then we take the derivative of the first, so that's plus 6x squared plus 4x times the second, f prime of x squared plus 2x. Then we come back here and take the first, so plus 2x cubed plus 2x squared times the derivative of the second. Okay, so what's the derivative of f prime? Well, the derivative of f prime is the derivative of the derivative, or the second derivative. So f double prime of x squared plus 2x, and not to forget, times the derivative of the inside, which is 2x plus 2. All right, done with derivatives. We're not done with the problem. Now we have to say, okay, we've now taken our derivatives. What's the next thing for us to do? The next thing is to plug in 1. Now you might say, wait, Steve, shouldn't we clean this up? Well, in some sense, here's my philosophy about when we should and should not clean things up. If we're going to do something with the computation, say like another derivative, then I think it's useful to clean up. But if our next step is to do an evaluation, I think you should not try to simplify before you evaluate. Why? Well, because right now you have things like multiplying polynomials together. That's not something which is necessarily trivial. It takes work. But once you evaluate, instead of multiplying polynomials, you're multiplying numbers, and that you can do. And so you're going to evaluate, pretty much my rule of thumb is evaluate as soon as you can, but not sooner. Because if you evaluate before you can, you're going to get the wrong answer. Usually you end up getting 0, and it's almost never going to be 0. Well, depending upon who your teacher is. Okay, so next stage, evaluate. And it's a good rule of thumb. Evaluate as soon as you can, but not sooner. All right, so we have 2. Now, x squared plus 2x, we're going to see that a lot. It's going to be 1 plus 2, which is 3. So 2 times f of 3 plus 2 times f prime of 3 times 2 plus 2, which is 4. So these are little multiplications here. Plus, and then here you have 10 times f prime of 3 plus, here you'll get 2 plus 2, which is 4, times f double prime of 3, because it's, again, x squared plus 2x is 3, times, and then you'll get 2 times 1 plus 2, which is another 4. Okay, but good news, we know these values. In particular, they're given to us up here. So we know, for instance, that f of 3 is 5, f prime of 3 is 2, there's actually 2 of those, and f double prime of 3 is 1. So we have 2 times 5, which is 10, 2 times 2 times 4, So that's going to be 16. Then we have 10 times 2, which is 20. Then 4 times 1 times 4 is another 16. So we get 16 and 16 make 32, plus another 10 plus 20 is 30. That gets us to 62. And there you go. Aha! Right? It just sort of flows out. Now, you might, at this point, say, hey, wait a second. All right, let's hear it out. What's your hey, wait a second? What about this data? We never used any of this information. It's like it was worthless. Is that a sign we did the problem wrong? No, not at all. You see, sometimes they'll give you more than you need. And in particular, they anticipate mistakes. When I say they, your professors, your teachers, instructors, whatever name they go by, they know what kind of mistakes people make. And so they're going to be like, well, let me have them dig their own grave. Of course, I wouldn't do that because, I love all my students. But some people are like, so what's a mistake that you might make? Let's be honest here. A mistake that people make is when they're applying the chain rule that they say, oh, I'm going to take the dirt of the inside and leave it inside. So in other words, they may have at some point had something like f prime of 2x plus 2 in a computation if they had done something wrong. And then they said, oh, well, do I have that? Oh, that's f prime of 4. So see, that extra information was given just for people who made a mistake. Although I think in this case, they didn't really need to do that because I think there were plenty of opportunities to make mistakes on this one, even if you didn't have that other opportunity with f prime of 2x plus 2. I know because this is one which I get it right about half the time. I'm pretty sure about this one because we worked through it carefully. And you really have to be careful. You have to be careful. You're never going to outgrow your silly mistakes. But okay, let's cross that out so nobody thinks that that was the correct thing to do. All right, on to the next one. Okay, this one. This one's a multi-part problem. And, all right, well, part A, write down both limit definitions of the derivative. Okay, all right, we can do that. So, what do we have? Well, so for part A, we could say that f prime of a, because that's the derivative, is the limit as h goes to 0, f of a plus h minus f of a all over h. Or you could say it's the limit as b goes to a of f of b minus f of a all over b minus a. In some sense, there's not a lot of work to be done here because this is just a, hey, do you remember what the definitions are? And of course, because we work and we're good students, we're going to remember that. Okay, part B. Okay, part A, we're done. Just do you recall? Part B. Find the derivative for the function x squared sine of x squared. And now you might be nervous. It's like, wait a second, do we have to use a limit definition? And it says, no. You don't have to use the limit definition on part B. So this is where we get to flex our new chain rule, right? Because we see x squared inside of sine. But what else do we see? And we see x squared times on the outside. So it's really a product rule and a chain rule in this problem. Okay, so here we go for part B. We can say our derivative, f prime of x, is product rule first, derivative of the first, 2x times the second, sine of x squared, plus the first, x squared, times the derivative of sine, which is cosine, leave the inside alone, times the derivative of the inside, which is 2x. If I wanted to, I could multiply the 2x times the x squared, and I don't know, I'll go ahead and do that. Plus 2x cubed cosine of x squared. Okay, so there we go. There's our derivative. Nice. Okay, so part B was pretty friendly. Now part C sort of makes you go, huh? Which is, it says, find a limit. Now, oftentimes, it turns out that when you have problems which have parts like A, B, C, that part C has some connection to parts A and B. Not always, but you should be thinking about that. And especially when it says, hint, compare it to parts A and B. Oh, it's like, okay, there must be something about parts A and B, because that's what the hint is kind of hinting at. Okay, so let's see what we have here. So we have our limit as t approaches 2 of t squared sine of t squared minus 4 sine of 4, all that divided by t minus 2. Like I said, if I just saw this limit on the wild, I may not immediately think this has anything to do with derivatives or with, in particular, the derivative of x squared sine of x squared. So let's see if we can now kind of piece together what's happening. I think if I'm looking at this, certainly the fact that it's a limit, I'm drawn to the limit definitions, and in particular, I'm more drawn towards the second one. And so what I want to do is I want to say, can I fit this into that? Well, I start saying, what would the pieces have to be? Well, let's see. If we made this B and A here, right? T goes to 2. Well, this is B minus A. All right. That's good. That's good. Now, what would that say? Well, we would hope that that means that this would be f of B, and we want this to be, this last piece here to be f of A. So, recall, of course, that B is what corresponds to t in this setup here. So it looks like we want to have f of t equal t squared sine of t squared. Let's see. So that would be f of b does become t squared sine of t squared. If I plug in a equals 2 into the function, I'll get 2 squared sine of 4. Okay, so that is f of 2. Okay, good. So we say, aha, this limit fits the mold for the limit of a derivative. And in particular, it fits the mold in the case for the function where our function is t squared sine of t squared, and the location where we're taking the derivative is at 2. So this limit is f prime of 2. So how do we find the limit now? Well, the answer is we don't take the limit. Now we say, hey, I know what this represents. This represents f prime of 2. I go to part B now. Part B says I have a formula for f prime of any value. So that means I also have a formula for f prime of 2. So we plug in 2. So what do we get? We'll get 2 times 2, which is 4, sine of 2 squared. So that would be sine of 4. And then 2 times 2 cubed. So that would be 2 times 8, which is 16, and cosine of 2 squared, which is 4. And there you go. That's the limit. In some sense, this is something that sometimes happens in mathematics where we're like, there's an expression we're trying to get our hands on, trying to understand more fully. And we don't quite have it yet. So the question is, can we relate this back to something we've learned? Well, we've learned about limits work really well when you have a difference of a function or a difference of an input. And so the key idea was to realize, hey, this limit, it's a strange looking limit, but it could be rewritten in the form of a difference of the outputs, f of b minus f of a over a difference in the inputs, b minus a. That's an interesting problem. Yeah, we probably wouldn't have guessed that, right, when you saw that limit initially, but we didn't have to guess because we could do the math. That's even better than guessing. It's ultra guessing, right? Okay. All right. So this one doesn't look so bad. And I think this sort of is a hint of things to come. So what do we have? Suppose that the depth of a pond in inches is measured by d of t is 45 plus 3 cosine pi 6t, where t is measured in months. What is the rate at which the water level is changing at t equals 4 months? And you got to include units. So what's happening here? So you have a pond, and I don't know exactly what the pond looks like. Of course, it looks very pond-like. So, okay, so I have a pond here. Now, there's some water in it. And, well, that's what ponds do. They have water. And so what's happening here is, depending upon the time of year, of course, how much rain you have, and so forth and so on. Well, if you have a lot of rain, the water level goes up. Maybe you don't have very much rain, lots of evaporation, the water level goes down. So over the course of a year, it's going to go up and down in some pattern. And so what we can do is we can model the depth of the pond by a function which has this sort of periodic going up and down type behavior. And so that's what this function does. See, the cosine, it's oscillating. All right, so what do we have? So our depth at a given time t is 45 plus 3 cosine of pi 6 times t. So if I'm looking for a rate, and I am, because I can tell I'm looking for a rate because it says the word rate. When we see the word rate, we say, hey, that means derivative. So if I want to understand what the rate is at time t equals 4 months, I say, hey, that really means figure out what the derivative is at time 4 months. So we're going to take the first derivative. That'll give us our rate of change. What happens to the 45? Constant. Goes away. Then we have 3. Derivative of cosine is negative sine. Leave the inside alone, pi 6t. Then we're going to times it by the derivative of the inside. The derivative of pi 6 times t is pi 6. So if we want to, we can clean it up. So we have a 3 times pi 6, and there's a negative, so we can say that's negative pi over 2 sine of pi over 6t. All right, so there's our answer. Okay, well, it's not our answer, that's our derivative. How do we find the rate at time 4? Well, that would be, what is d prime at 4? So that would be negative pi over 2, then sine of pi over 6 times 4. So that's negative pi over 2 times sine of 2 pi thirds. Now, what do we know about sine of 2 pi thirds? Well, let's draw a quick picture. Now, if you're not comfortable with 2 pi thirds, I can tell you that that's the same as 120 degrees. And if you're still not comfortable with 120 degrees, I can tell you it's over here. This is roughly where 2 pi thirds is at. Now, if we're looking for sine of 2 pi thirds, well, that would be the y value. So, what can we say about the y value at this location at sine of 2 pi thirds? Do you know it? Okay, this one is a little bit maybe not so obvious. I will point out that if you were to stay at the same height, that it's the same as sine of pi thirds. You might be a little more comfortable with sine of pi thirds. And do you know that one? All right, so it is square root of 3 over 2. So square root of 3 over 2. So when we multiply this together, what do we end up with? Well, we end up with minus pi root 3 over 4, the 2 times 2. Now, are we done? And why not? Well, it said to include units. So, what units are attached to this number? Because this is a rate, and rates have units because it's rates of change are how something changes with respect to something else. So the top is change in the output. So that's, what are the units of D? Well, it's the depth in inches. So inches per, and the denominator are the units of the input. In our case, T. So how do we measure time? Well, it says here, time is measured in months. So inches per month. So it's going down. Now, you might say it is changing at negative pi root 3 over 4 inches per month, or you could also say the following statement out loud, decreasing at pi root 3 over 4 inches per month. Now, does this still mean the same thing? Well, yes, because decreasing is an indication that you are negative. It's a negative rate. All right. Now, that's the first question. Notice there are two questions here. And the second question is, should we expect that rate to increase or decrease? So in other words, we have a rate, and we want to know, is our rate going up or is our rate going down? So we might be thinking to ourselves, wait, what does it mean? So oftentimes when we think about is something increasing or decreasing, we're like, oh, that means it's like a rate, right? Okay, positive rate means we're increasing, negative rate means we're decreasing. So in some sense, what we're trying to get at here is what can we say about the rate of the rate? So where do we need to look if I want to understand how the rate of the rate is changing? I have to look at the second derivative. Okay, so to answer the second part of this problem, we're going to look at the second derivative. So let's look at our d double prime. So the constant stays there, and then we have the derivative of sine is cosine, and then we have the inside stays the same times the derivative of the inside, pi over 6. Now, what do I care about? Well, what I care about is what's happening with whether it's increasing or decreasing. So this is negative pi squared over 12 and cosine. And let's plug in 4. So cosine pi 6 times 4 is, again, it is 2 pi over 3. Okay, so what's happening here? All right. Our cosine is our x value. So cosine 2 pi thirds, this part right here is it's a negative value. Okay, so a negative times a negative means that the second derivative at 4 is a positive value. All right, now comes the interesting question, the interesting dilemma. And you might think, there doesn't feel like there's a dilemma here. We figured it out. The rate of change of the rate is positive. So that should mean that our rate is going to increase. Absolutely, if we are careful with what we mean by it's increasing. So here's why it gets dicey as how to answer the question. And I wish I could say that there's an unambiguous way that everyone will be confident of that won't make people say, well, wait, hold on, don't you mean? Here's the problem. We currently have a negative rate for how the water level is changing. So the water level is going down. So when we say that the second derivative is positive, what's going to happen is that this negative value, it will still be negative, but it'll be less negative. In other words, however much it's dropping, it's going to be dropping less. So by that idea, we could say, well, the rate is increasing. But of course, because of the fact that we have different signs, it gets confusing. If we were to think about it phrased as the decreasing pi root 3 over 4 inches per month. Here is where it gets kind of curious. It's still going to be decreasing, but what's going to happen is that this value will go down. So, in other words, it'll keep, in a very short time later. So if you look at, 4.1 months or something, the water level will still be dropping, but the rate at which it'll dropping will have a smaller value. Okay, so do you understand what I'm trying to say? Oh, I think I'm confusing myself more than I'm confusing you. So what's going to happen is that our overall rate, including the sign, will increase, but in terms of the magnitude of the rate will decrease. And this comes down to pay attention to your signs. So you got to be careful whenever you have signs coming into play. It can be a little bit confusing. If my explanation hasn't demonstrated that, I don't know what will. Okay, all right, good. All right, now ready for the next one, right? All right, here we go. For the functions f of x and g of x, we have the following information about the tangent line. So I have a bunch of different tangent lines at various points. So at 1, 2, 3, and 4, I have the tangent line to f and the tangent line to g. And now it's asking us to find the following tangent lines. So I have to find two different tangent lines where I'm creating this new function by doing some strange combinations to f and g. Well, this should be interesting. Okay, how do we approach this? Well, one way to think about it, whenever we're looking for a tangent line, it really says I need to understand things such as what's the value of the function at the point, what's the derivative at the point. So for instance, in part A, because we're finding a tangent line for h of x at 2, that really says I need to find what is h of 2 and h prime of 2. That's what I'm after. Now in part B, it's a different function. It's a different h of x. And here's a different point. So for that h of x, we're after h of 3 and h prime of 3. But again, these h's are different depending upon whether we're doing part A or part B. So what's going to happen? Well, what's going to happen is we're going to need to use information about f and g. We don't actually know what f and g are, but we've been told about tangent lines. Now, tangent lines are ways of storing information about f and g. And in particular, I can now conclude what's the value of f and f prime and g prime at the points 1, 2, 3, 4. And I can read it off from the tangent line. So if I were to take this data, I could take this chart here and transform it to a new chart. This is what the chart would look like. So I could say x equals 1, x equals 2, x equals 3, x equals 4, and here we go. And then we're going to have our f of x, our f prime of x, our g of x, and our g prime of x. So my claim is we can fill this chart in. So let's just do it really quickly. So then we just have the chart to refer to, and that should hopefully make things go faster. So how do I find f of 1? Well, what I do is I come to the tangent line at 1 and I plug it in. So plug in 1, 6 minus 5 is 1. Okay, at 2, plug 2 into the tangent line. 4 minus 6, that's negative 2. 3 is 1 plus 7. Sorry, 1 plus 6, which is 7. 4, 3 plus 4, also 7. Okay, f prime. How do I find f prime? Well, the slopes of the tangent lines are the derivatives. So I can just read off the numbers here. So negative 5, negative 3, 2, 1. Okay, how about g? So g of 1, 2 plus 4, 6. At 2, 5 plus 2, 7. At 3, 7 minus 6, 1. At 4, 9 minus 12, negative 3. And the slopes are the derivatives. So 2, 1, minus 2, minus 3. 2, 1, minus 2, minus 3. So here's the thing, is this chart gives us as much information as that chart, because I can jump back and forth between these two charts. They have as much information about the function as the other do. Okay, so now that I have that, I get to start sort of playing around. So let's start with part A. All right, so first off, let's find out what h of 2 is. So we plug in x equals 2. We're going to get f of 2 squared, so that's f of 4 times g of 2 squared. So we say, well, what is f of 4? That would be 7. G of 2. So g of 2 is 1. So 1 squared. So h of 2 is 7. Now, for h prime of 2, we first should find h prime of x. So h prime of x, we're going to do a product rule and then chain rules. So the derivative of the first. So derivative of the outside, inside stays the same times the derivative of the inside, then times the second, g of x squared, plus the first, f of x squared, times the root of the second. Now here, g of x is the inside function. The square function is the outside function. So the 2 comes down, g of x to the 1 power times the derivative of g of x. That's g prime of x. All right, so that's our derivative for h. So now we plug in 2. So h prime of 2 would be f prime of 2 squared, so that's f prime of 4, then times 2 times 2, which is 4, times g of 2 squared, plus, then we're going to have f of 4 times 2 times g of 2 times g prime of 2. Now we just need to go and read off all these pieces of information. F prime of 4 is 1. Oh, that's nice. Times 4. G of 2 is 7. Really? Oh. It's, Wait, am I reading that right? Oh, did I make a mistake here? I made a mistake up here. I put in g prime of 2, not g of 2. Ha 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 ha. That's okay. We can fix that. So it should have been f of 4 is 7, and g of 2 is 7. So that should have been a 7 squared. I am so sorry about that. Of course, 7 times 7 squared is 343. There we go. Yeah, now we're back on track. So 1 times 4 times 7 squared plus f of 4. Yeah, g of 2, wow, that's a big number. Well, you know, sometimes they are what they are, right? So what is f of 4? F of 4 is 7 times 2 times g of 2, which is 7. And then g prime of 2? Well, g prime of 2 is 1. Okay, now, this looks complicated, but notice what can you do? You can actually pull out a 7 squared, because both of them have 7 squared. So it's 7 squared, and then it's what? It's 4 plus 2. So that would be 6, because you get 4 from the first term, and then 2 from the last. And if you take 7 squared times 6, that would be 49 times 6, which is 240, plus 54, which makes that 294. All right, so now I have h of 2, I have h prime of 2, so I can conclude that y minus my y value is equal to my slope, 294, times x minus my x value, 2. And I think I'm going to leave it in that format. So, after all, that is the right line, so it's okay for us to leave it that way. All right, that was part A. Now, let's see what joys await for us in part B. Well, for part B, similar process. So here we're going to plug in 3. So h of 3, that's f of g of 3 plus 3 times f of 3. So we go through this. What is g of 3? This time, I'll try to read the right slot. So g of 3 is 1. Okay, so g of 3 is 1, and then f of 1 is 1. So this is 1 plus 3 times, and f of 3 is 7. So 1 plus 3 times 7 makes that 22. Okay, now take a derivative. H prime of x is f prime of g of x times g prime of x plus product rule. Root of the first would be 1 times the second, so plus f of x plus the first times the dirt of the second. Now we're going to plug in 3. So h prime of 3 is f prime of g of 3 times g prime of 3 plus f of 3 plus 3f prime of 3. Good. Now we'll start working our way through this. So g of 3 is still 1. That's good. F prime of 1 is negative 5. So we get negative 5. G prime of 3 is negative 2. So negative 5 times negative 2 plus f of 3 is 7. And then f prime of 3 is 2. So plus 3 times 2, which is 6. So I have 10 plus 7 plus 6 makes this 23. So 22 and 23. All right, so now I do a similar thing. And I can say the following. Well, I can say y minus the y value, so 22, is equal to my slope, 23, times x minus my x value. So x minus 3. And I'm satisfied with that answer. Right? Good. Whew. Ah, that's some work. That's some work. But on the other hand, if you really understand what's going on, is it's not so bad. Because what did we do? Well, we said, look, I have information about my tangent lines, which is storing information about my functions, f and g. Now I'm going to create new functions by combining f and g in various ways. So let's find those tangent lines. And of course, we probably could have found a lot more things if we dug around, but that's all we're asked to find for now. So let's move on to the next one. All right, let's do one last one. Okay, hopefully it's a good one. So, given that f of x and g of x are differentiable, and we know the product is h of x, and the composition f of g of x, we'll call that k of x, and we have a bunch of data. So we have what happens to f and g and h prime and k prime and so forth and so on at some points. So we're missing a lot of data here. Now let's be careful about how we read this chart. So what's happening here is this first column is telling us our xi. So this is x equals 2, x equals 3. So for instance, I know what f of 2 is. So, okay, that gives me some information to work with. I can also know what g prime of 3 is. So g prime of 3 is negative 3. So the question is, how can we take the information that we know and figure out the information that we're missing? Now, in some sense, the important parts are the first. See, if I know the stuff at the beginning, the stuff at the end will pop out automatically. So I want to sort of work on the end parts first, because I suspect that's where I might be getting the most information. Because h and k, these functions, really have something to do with what's happening with our f and g. So oftentimes we can probably extract information from these values which we already know to help fill in here, and of course we can jump back and forth as we need. Now I think it'll be helpful for reference for us to write down what various things are. So in particular, what is h prime and k prime? So h prime of x would be f prime of x times g of x, then plus f of x times g prime of x. That's our product rule. And k prime of x is f prime of g of x times g prime of x. That's our chain rule. Okay, so now we need to start searching around, digging around, and see what we can find. Okay, so what do we have? Well, let's start with just h of 2, right? So h of 2. So we know that negative 3 is equal to h of 2. By definition, that's f of 2 times g of 2. Now, do I know either of those? Well, I know f of 2. That's this entry. So that's minus 1 times g of 2. So, well, if negative 3 is minus g of 2, that says, hey, I know what g of 2 is. That's got to be 3. All right, good. So we've now found g of 2. Okay, progress. All right. So I'm just going to put a little check mark here that says I've used that piece of information, so we don't have to go back and say, I wonder if this will help us now. Well, we've got it down as far as we can go. How about h prime of 2? So we can say that 2, sorry, it's not h prime of 2, it's h prime of 3, right? Because there we go. So 2 is equal to h prime of 3, and that's equal to f prime of 3, g of 3, plus f of 3, g prime of 3. But I have a lot of information about what happens at 3. So let's put in what we know. So for instance, f prime of 3 is 7, and g of 3 is 2. So this will be 7, this will be 2. F of 3, that's missing. G prime of 3, that's not missing, that's negative 3. So this is 14 minus 3 f of 3. And again, that equals 2. So if you rearrange that, so for example, move the 3f of 3 across, move the 2 across, 3 times f of 3 would be 12, which tells us that f of 3 has to be 4. Okay, so f of 3 is 4. We now know that entry. And I'm going to put a little check to say I've used that piece of information. See, if I keep track of what information I've used, then I don't have to say, I wonder if I can get more. No. We've gone as much as we possibly can. There is no more information for us to glean from that particular data entry. All right, well, let's try another data entry. Well, what can we try? Well, we could try kappa prime. So kappa prime of 2. I call it kappa. K, kappa. All right, so 42 is equal to k prime of 2. Now, k prime, that's f prime of g of 2 times g prime of 2. Now, let's think about what do we know. Do we know anything? Well, we do know what g of 2 is. We actually found it here. See, g of 2 is 3. So this is f prime of 3 times g prime of 2. Well, we don't know what g prime of 2 is, but do we know f prime of 3? Well, we do know f prime of 3. See, f prime of 3 is 7. So this is 7 times g prime of 2. So 42 is 7 times g prime of 2. Well, that tells us that g prime of 2 has to be 6. All right, so g prime of 2, here we go, there's 2, g prime. So that entry there is a 6. And we've used the 42. All right, good. Well, we're on a roll. We're making great progress here. We're making wonderful progress. And let's see. Let's try to use this entry here. So negative 15 is equal to k prime of 3. See, there's negative 15 is k prime of 3. So that is f prime of g of 3 times g prime of 3. Just plugging 3 into our derivative. Now, do we know what g of 3 is? Well, we do know what g of 3 is. G of 3 is 2. So this is f prime of 2. G prime of 3, well, g prime of 3 is negative 3. So negative 15 is f prime of 2 times negative 3. So that tells us here, well, that f prime of 2 has to be 5. Okay, so that means that is a 5. And now we've used that piece of information. But now, here's the important thing. Aha, see, we're in a great shape right now because we filled in all the information about f and g. And h is really combinations of f and g. So we can now finish our last bits of our table. So for instance, what if I want to know h of 3? So what is h of 3? H of 3 is equal to, see, h is f times g. So it's f of 3 times g of 3. So that would be 4 times 2. 4 times 2, which is 8. So there we go. That's 8. And finally, we get to our last little piece, which is we need to know h prime of 2. So h prime of 2 is, according to the rule, see here's our h prime, that's f prime of 2 times g of 2 plus f of 2 times g prime of 2. So f prime of 2 is 5, and g of 2 is 3. So we have 5 times 3 plus f of 2 is negative 1, and g of 2, f of 2 is negative 1, g prime of 2 is 6. So 5 times 3 is 15, minus 1 times 6 is minus 6. 15 minus 6 leaves us with 9, which means that goes there. And we've filled it in. That's it. That's the whole table. We were able to figure it out. So even though we were missing a lot of entries, there were relationships between the functions which let us put it all together. A fun little puzzle type problem. You know, it's like, okay, here's what I know. Can I use that to figure out what I don't know? And I think actually some of the students who do best in calculus are people who say, hey, I'm not going to look at these as like these burdensome problems, like, oh my gosh, another problem. They're going to say, ooh, a puzzle. Let me think about this one. I want to solve this puzzle. And if you can come in with that attitude, wow, it really helps. It helps a lot. All right, well, wow, lots of practice today. Well, today was a big day. Chain rule, very important. So we probably won't have as much practice in the future sessions, at least not for a while. But practice is always important. And thank you for coming to practice with me today. All right, have a good day.